Autonomy. It's my great pleasure to welcome Kevin Tran, who will be talking today. He's a senior research scientist at Toyota Research Institute. He previously worked in, had a short stint at Schrödinger, I believe, which is a company, material science division of this company. And then he did his PhD in chemical engineering at Carnegie Mellon, working in green chemistry and finding, searching actively for sustainable catalysis. And during his research, he developed some and has some very successful projects in applying and searching for catalysis using machine learning. So I'm extremely glad to have such a real world application here and a real success story here presented. So off you go, Kevin. Thank you.
Thank you. Before I start, I also want to mention that I encourage interaction and discussion throughout the presentation. I would rather tailor the talk to what folks here are interested in than just going through the spiel. So please speak up at any point, and I will happily answer any questions here. All right. So normally the first slide for sustainable energy talk is some hockey sticker around global temperatures and time. I figured I'd put a little different spin on it this time, right? So instead we have a plot of extinction rates over time of various species, right? And even if you're not an animal activist, this is a pretty important topic because environments, the way I see it, are a lot like Jenga towers, right? So each row on a Jenga tower is an environmental niche, right? So one row could be plant matter, another row could be predators, another row is insects and herbivores, etc. And what's good about healthy ecosystems is that each niche can have several blocks, and each block here can be different species, right? So there could be several predators, several herbivores, etc. And so if you kill off one species, there's still all these species there to fill that role, right? The issue is the more species that go extinct, the more the Jenga tower starts looking sparse, right? And what could happen eventually is one entire row could fall out and the thing can collapse. And this isn't just theory. This has already happened. For example, in some environments, for safety reasons, humans killed off all the wolves. And that environment happened to have only one block in that row. And we knocked that out, we killed the wolves. And all of a sudden, a lot of the grazing animals, such as the deer, actually just started overgrazing all the grass. And what happened there is they pulled out all the grass near the river in this forest, and all the water that normally flows through it and stays and is maintained by the root systems of the grass just flows away instead. And it goes from a lush forest in the woods to just a dry desert, right? And so the entire ecosystem just collapses from removing one species, right? We are doing this across the entire world right now. A lot of the things are changing so fast, animals can't keep up, and we're destroying entire environments, which could in turn make it hard for humans to farm in certain areas, right? And so this isn't just an animal ecological thing. This is a human issue, right? One of the ways we can slow down climate change is by just using sustainable energies, right? And here's a plot that kind of has a rough approximation of how much energy we can get from different sources, right? So outside here, we have things like coal, petroleum, natural gas, and this has a very rough estimate of how much energy we have left, right? These estimates are kind of old. There's lots of grains of salt to be taken here, but the gist is the order of magnitudes here are still pretty close to what we think today. And we can see solar plays a huge part of the energy that we could possibly get, right? The issue with solar is that it's only here during the day, but at night we need to turn on all our lights, right? And so we need to find a way to store this energy. One way to do it is, instead of through batteries, is through something called solar fuels and chemicals, right? So to understand this, we can look at just fire, right? So with fire, we're normally burning what we call hydrocarbons, or materials with carbon and hydrogen. Oxygen needs to be present, and when we burn them, we get water, carbon dioxide, and energy in the form of heat. Solar fuels are really the idea of turning this process backwards, right? So we have our fuel, we burn it, we put it in our cars, we drive our cars, and we get CO2 and water out. What if we just take this solar energy put it back into chemical bonds and convert these back into fuels or chemicals. And this is the idea of solar fuels, that we can create a circular ecosystem where we don't have to keep pulling out fuels from the ground, right? It doesn't end with just fuels either. We can also make hydrogen for fuel cells. We can even make fertilizer to feed the world. And this can even prop up the entire chemical ecosystem in our economy, right? And so this has a potential to really kind of change the way we make things in the world. The issue right now is that this step of going from simple things like carbon dioxide, water, and nitrogen over to useful chemicals is not economically viable. For instance, our factories we need would be too big, or the energy we get in, we get out doesn't equal the energy we get in, or it's just uneconomical, right? And so what we really need to do is find better catalysts to drive these reactions to make them more economical, so we can actually use them. Right? And one useful way to look at this, in my opinion, is through what's called a stage gate process, and this is very common in product development, right? And so the way products are normally developed, we have lots of ideas, probably hundreds of thousands or whatever, and most of them are bad, and some of them are worthwhile to go into the lab and test them out. And in the lab, we find, okay, some of those might not work very well, they're not efficient enough, and then this goes down the funnel to, okay, some are good enough, and we design a process and scale it up, et cetera. In the tech space, this can happen in weeks or months, but in the manufacturing space, this can take several years, like 2 to 10 is a very rough estimate. If you look at biology or pharmaceuticals, that can be even decades long process, right? And really for solar fuels, we are somewhere around here, maybe here, right? And the reason I say this will be very important later on to realize that and expect that we're not really trying to scale up and optimize something. We're really trying to generate ideas faster, right? And so we'll come back to this a little more later. And here's just some examples to make this idea a little more concrete. So early on, we have an idea of making solar fuels. And currently, we're in the process of testing them in labs. Eventually, we want to scale them up to factories. And then from the factories, you can eventually sell fuel cell cars to folks and stuff like that. Yeah. Are there any questions before I get to more outlines? So the rest of what I'll be discussing today is I'll be doing a little bit of a deeper dive into some of the work that I did when I was still in grad school, or using active learning to discover some of these catalysts. For me, I've been at Toyota for about half a year now, and so a lot of the work I have is still kind of pending, or some of it's under NDA, et cetera. So I can't share too much of what I've done very recently, which is why I focus on some of this work. What I can share is some of the recent trends in the materials informatics community, specifically tailored around trends with active learning itself. And then at the end, I have a few talking points to open up discussions here around things that we can actually do to push this field forward. Right? So let's get into the first case study here. So we need a little more background before we get into the actual algorithm here. So first, just kind of recognizing that chemical reactions are pretty complicated, right? So even if we want to turn CO2 into something like simple, like methane, right? When we actually look at the reaction that's happening, it actually is a series of several steps. So first, CO2 has to adsorb onto a catalyst here, in this case, it'll be copper. And then we have to add a hydrogen and then remove this oxygen, hydrogen, et cetera, and go through this entire chain of reactions to get methane out. This is a lot of information to look at. One of the ways we can simplify it is by actually doing an energetic analysis. So here is another plot where on the y-axis, we have how much energy is stored in a particular state, right? So each column, this column is how much energy is a reference energy for carbon dioxide, and then this column is reference energy for this system, et cetera, et cetera. And the x-axis is just what we call coordination. This is effectively just kind of the state of the system, right? So let's focus on the black here. And from chemistry, one of the things we know that is the lower the energy, the better, or the more negative, the better, the more stable it is, right? And so if we look at this series of black reactions, every time we jump up, this is kind of like throwing the ball up a hill. It takes energy. Every time you fall down, it's like rolling the ball downhill. It's spontaneous, it's easy, right? And so when you have a long string of these kind of reactions, instead of trying to study all of them, we can actually just study the one that is the most uphill, we call it, or we have to throw the ball up the farthest, right? And so this will be akin to the rate limiting step. So if we really kind of find a way to make this as fast as possible, everything else kind of falls through the cracks. And really, this is what we can focus on. How that manifests is into something called a volcano diagram, right? It's volcano because it's shaped like a mountain, and I guess volcanoes are a cooler sounding version of mountain, right? So on the y-axis, we have the logarithm of the reaction rate. So we want these reactions to go faster. On the x-axis, it's the absorption or binding energy of a molecule. In this case, it'll be carbon monoxide here, right? Which is this molecule. It turns out there's sort of a Goldilocks effect, exemplified by this volcano, right? So if carbon monoxide binds very strongly, what that means, if we look back here, is if this is very low, then usually what that means is carbon monoxide really wants to stick to the surface, but carbon monoxide looks a lot like the rest of the things in this entire reaction network, right? And if this wants to stick very strongly, then there's a good chance that this also wants to stick very strongly. And if this sticks here, it never comes off the surface and never actually becomes a product. It just kind of sits there and does nothing, right? And so we don't actually get methane out. We just get a bunch of stuff on copper, and that's not useful for us. If we go to the other end, the far right side, where the binding energy is very positive, then what that usually means is carbon monoxide may form, but then it immediately pops up. It never goes to the next step. It just desorbs immediately, right? So we never actually make methane. We make carbon monoxide, which is also not good. And so there's a Goldilocks effect where we have to be in the middle, where we want an absorption energy around right here so that we can actually have carbon monoxide come to the surface and react, and then the methane can pop off, right? Are there any questions there? All right, so that kind of begs the question, how do we actually calculate these binding energies? One way we can do them is by using something called density functional theory, or DFT. With DFT, it's just really a computer simulation of molecules, right? And so what we do in this case is, let's say we start with platinum, right? What we have to do is figure out what surface of platinum we're actually going to be having this reaction happen on, right? So this can be the top, the side, the front, some diagonal cut. We just choose one of the surfaces. Once we do that, we have to figure out, okay, where are the molecules going to be sitting? They can be right on top of one platinum. They can be in between two platinums. They can be in between four of them. So we have to enumerate all these, what we call absorption sites. Once you do that, then we can put the molecule, in this case hydrogen, on top of the surface, and then we can calculate the absorption energy or binding energy, and then put them into these volcano diagrams, which the field has been building in the past few decades, right? And that's kind of the background of catalysis here. So really, we're looking for catalysts, as in surfaces here, whose binding energy is at some Goldilocks optimum level here. All right, now we can get into, oh, go ahead.
Can I ask a quick question? So this is everything in simulation, but so
Yes.
What is kind of the general practice here, that this simulation is sufficiently accurate for the real experiment? Is this the consensus, or because you could do this somehow also in, you could also perform this experiment, I guess, where you
absolutely
where you order
yes,
these
yes.
catalysts
Yes.
and
Yep. Generally, these simulations are currently treated as correlated with experiments, but not indicative, if that makes sense. And so, like the gold standard is we do the experiments, but the experiments can, it takes a long time to set it up in the lab and run them, So we can get maybe, depending on the lab, dozens or hundreds of tests in a year for that. But in simulations, I mean, we can just rent more servers or get more AWS credits. So we can run thousands or tens of thousands or more of these at a time. And so typically these simulations are used as a pre-filter for experiments. So we run a bunch of simulations, we narrow it down from thousands of candidates down to a dozen or so, and then we pass that down to the labs and they go take it from there.
I see. Okay.
Yeah. Good question. All right, so now we get into some of the active learning work. Oh yeah, go ahead, please.
I had thank you for your talk. I had a question regarding the adsorption sites.
Yes.
Because I'm wondering how, so let's say we have those 3 binding sites or adsorption sites, and they are ranked. One is probably has a lower energy than the others, and so on.
Yep.
And so I was wondering if the reaction rate was driven by, the single best or the average or, the worst, or like, what does that, what's the correlation between the distribution of the energy of the binding sites and the, can you just look at the best and say, well, I've found a great binding site and, that's going to make a great catalyst? Or do you also have to make sure that the others are not too bad and stuff like that?
That is a very excellent and astute question. The robust answer is it depends. The shortcut answer is we found some experimental evidence showing that the strongest binding site generally is the one that's more indicative of the surface. But again, there's a lot of caveats there, and it depends. And without going into too much detail, that's my shorter answer.
Okay, thank you.
Yeah, but I mean, sometimes, there's a lot of factors, and this is an entire subfield, so it's hard to not go into too much detail. But yeah, it just depends.
Thank you.
Yep. Any other questions? And this is also a very important point later in the talk, so good segue. All right. So now to get to active learning. First, what our group had to do was really automate the simulation process, right? And so this alone is a non-trivial amount of work because we wanted to look at many, many, many calculations. And so we had to just really build a software platform to actually perform these in a high throughput manner. When I say high throughput, I mean running thousands, tens of thousands of these at a time. And so we can't do that by hand. And so we just spent 1.5 years or 2 years or so at building this out, right? And you can read about this in this paper. Once we had that, we said, okay, what do we want to start running? And so what we did is we took a database of materials from what's called Materials Project, and then we got these 3D structures from them. And then we went ahead and did the work of enumerating the surfaces and absorption sites. We took what we consider a small slice of the database, just to try and be conservative and limit us here. And then once we went through this process, we found around 16 million absorption sites. And to give you an idea, each of these single calculations takes anywhere from hours to days, sometimes more. So you multiply that by 16 million, that's on the order of centuries of computation time. And yes, we can throw more computers at it, but those aren't free. And at the same time, we have a really, really large search space here. Like I said, we took a very small slice here. And so the gist is we're never going to do all these calculations. So we have to pick them intelligently, right? And that's where the active learning comes in. So our first algorithm, retrospectively to me, is embarrassingly naive. But at the time, we had me and my advisor. And with a 2-man team, we didn't have the engineering to do everything the perfect way. And so we put together a minimum working example and then decided to go improve upon it later, right? Luckily, the minimum working example worked out. So what we did is we first had to build a surrogate model for our active learning loop. And so we just used TPOT, which is a genetic algorithm platform to just really build models, right? And so we had a semi-hacky way to featureize our 3D structures, put them in the teapot, train an ML model, and just use that. And then we took our database of absorption sites and just predicted the binding energy of all the sites. And then we have a distribution here, right? So in this case, we have a distribution of carbon monoxide binding energies. And then here's where the really hacky part starts. We knew that we wanted an energy around right here, around -0.6. And so we just drew a bell curve here. And then we multiplied each absorption site by the value of this PDF of this Gaussian curve. So we essentially projected our distribution onto a bell curve, and then we sampled from these values. What this effectively did was it really focused and gave a high propensity for us to select absorption or sites that were close to this optimal, but still allowed us to some room to really explore other sites in other locations. I'm not sure how well I explained this. Are there any questions here? Okay, cool. One of the nice things about this is that we didn't need any uncertainties. One of the bad things about this is it's very hacky and it has no fundamental grounding. It's just what we did to get stuff running. And so we did that, we closed the loop and we left it running for months at a time. And then eventually came a point where we really needed to ingest our data and predictions. And so here's where we turned to t-SNE, right? And so we did t-SNE, and then we kind of color-coded it by the binding energy, right? And so black is too strong, pink is too weak, purple is just right. And then within each of the clusters, I had to go through by hand and look at each of these data points, which corresponded to different structures, and try and look for patterns in the data points. And we found that certain alloy blends started showing up a lot with these purple islands here, copper aluminum, copper gallium, et cetera, et cetera. And this is the point where we turned to collaborators and said, hey, do you guys want to try any of these, right? Luckily, to make a long story short, one of them, copper aluminum, actually worked out. And so we had collaborators at the University of Toronto, Ted Sargent here with his postdoc at the time, Miao Zhang, tested this, and it actually worked out really well. And they were actually able to turn carbon dioxide into ethylene at record efficiencies, which was really good. Eventually, they had other issues, and I forget exactly. I believe the selectivity, as in like was good, as in like we were able to make specifically ethylene and not other products, which is really difficult. But the energetic efficiency was a little bit too low at the time, and so we're still looking for new things here. But the thing is, even that first step of finding something selective was pretty difficult at the time, right? And so this is actually a success in our mind, showing that this had the running to work, right? And so from there, we got to the point, okay, our minimum working example surprisingly worked. Let's see what we can do to improve it. The first thing I did was stare at this thing, right? So I don't know how many people have run t-SNE, but at the time, it didn't scale very well. It took dozens of minutes, sometimes an hour on our ever-growing data set of tens of thousands of points. It was also stochastic, right? And so sometimes you just have this shotgun here, and other times segments wouldn't really separate. And also, like I said, I had to go through each of these clusters by hand and kind of mouse over them and see what the material was and say, oh, this is copper aluminum, oh, this is copper gallium. And this is just not sustainable when we're getting new data every single day, right? And we can't rerun t-SNE, have me sit in front of the computer every day. And so we needed a way to really automate this process. And so really that's what we started thinking about. Like, okay, instead of having a pile of data, how we can actually like convert that to recommendations. Really what our issue was bridging the gap between our atomic scale simulations and our micro and macro scale experiments, right? So we started thinking about this, and this comes down to Victor's very astute question. Eventually we hypothesized that a multi-scale model could possibly connect our atomic scale simulations up to the bulk catalyst here, right? So the gist here is that, let's say we have a surface, right? And it has multiple absorption sites, like Victor was saying. Each of these sites, we can make a prediction with an ML model. And let's say each of these dashed lines is the distribution of that prediction. So at this point, I'm skipping along. We now have an ML model within SIMT, right? So we have that distribution of energies for one particular site, and we can have several of those. So 3 sites, 3 dashed distributions here. There was experimental data suggesting that the strongest binding site actually matters the most, and all the rest of these actually matter less. And so as a pooling operator for a surface, we we discarded these higher binding sites and just took the lowest one. And then this is our distribution of binding energies for a surface. Now, how do we pull surfaces together into a bulk? Our naive solution here was just to average them, right? And so that'll get us an average binding energy of a bulk. But then we don't really care about binding energy. We care about what we call the activity, or how fast the reactions can actually happen. And so we had to map that through our volcano diagram, where we input the energy and output the activity here. And now we have a distribution of the activity of a catalyst. And so this is our kind of multi-scale way of going from atomic scale to the bulk level. The question is, how do you turn this into an active learning loop? This is where I worked with Willie, our very own Willie here, to design what we call the Myopic Multiscale Sampling strategy, right? And so what we realized is that at the lowest level, we were really just trying to find the most negative binding site on the surface. And really, if we were looking for most negative, that's an optimization problem, right? And so here, we're effectively just doing Bayesian optimization. At the surface level, since we're taking the averages of several surfaces to pull together into a catalyst, we really want an accurate estimate of all the surfaces. But obviously, we're not going to sample every single cell in every single surface, right? And so really, we're just trying to get a good model here. And so here is where we turn to uncertainty sampling, where we're trying to minimize the variance in our predictions of these energies. Once we get to the top level of trying to recommend catalysts, we realize that most people in the field really turn to optimization. They're trying to find the best catalyst. But if you turn back to the idea of where we are in the product pipeline, right? We're not at the optimization stage. We're really still ideating, trying to get more ideas of different catalysts, and we know we're going to fail often. So the idea is to fail faster, not to find the best, but to fail fast, because something else crazy is going to happen. It's going to interrupt us. And so really that allows us to relax this algorithm from an optimization to a level set, right? We're really just trying to find things that are good enough to recommend to experimentalists to try, right? And so this is eventually what we put together. So during every simulation loop, we got more absorption sites. We retrained our ML model, regenerated all of our predicted activities for the catalysts, right? And then we have those. And then of these, we tried to find the ones that we weren't sure were good or bad. We selected those. Once we selected that catalyst, now we have to decide which surface we're going to sample. We sampled the surface that we thought had the most uncertainty. So in this case, it'll be the blue one here. Once we have a surface, we wanted to sample the site that we thought was the most negative. And so we sampled this guy here. Does that make sense to everyone?
So you went from top to down, right, when you selected?
For the acquisition, correct.
For the acquisition. And the top is essentially a cluster point.
Yes.
In this T-SNE, right?
Yeah, that's what we're shooting for. Yes, exactly.
But it is actually the T-SNE cluster or not really?
Oh, no, it was not actually a T-SNE cluster. The T-SNE clusters were, let's show it here. Like for, what was over here?
So you simply had like a label to each, like copper, gallium, comma this site,
yeah,
comma. Okay.
it wasn't these clusters. We had, our label was what we called the bulk, what we call the bulk, right? So each one of these could have several surfaces and several sites. The T-SNE clusters was actually a superset of this, right? So imagine there's a certain ratio of these oranges to grays to purples, right? Mm-hmm. Imagine we have half the oranges here, right? And it's effectively the same elements, but in different ratios. So in T-SNE, we found that those kind of grouped together in their own clusters, right? But for our selection algorithm, we didn't go by the T-SNE clusters. We went by these bulk structures. So we kind of selected, okay, we're going to have this ratio of elements, not the other ones.
Okay, now that's it. But in order to get the similar explainability that you can get from the T-SNE, you would really want to see the combination of how these things kind of get together, right?
Absolutely.
In your sampling, you don't have that yet, right?
Yes. That was solved by a different type of visualization that I did not put in the presentation. Effectively, what we did is we made a grid plot of all the different alloys we can have, and then we effectively made our manual t-SNE. And we realized that like what we found value out of the t-SNE was separating these different alloys. It's not just this ratio, but like really it's something with copper and aluminum. And so we just plotted those clusters ourselves.
So manual meaning that you chose the features of which you kind of do the clustering, kind of, or the bucketing.
We manually made clusters, right? And so there was no t-SNE. We just had a plot where we just kind of piled in all the copper lumens together. We piled in all the silver palladiums and then color coded them exactly like we did before. And then scaled them to the correct size, so more data is bigger and stuff. So I didn't have that as a backup slide here, but we eventually just did away with t-SNE and did the visualization manually ourselves. All right. So we designed this acquisition function, and before we hooked it up to the big machine, we decided to test it in silico, right? But what I mean by that is we didn't actually do any more DFT calculations. We took our database of the things we had already and wanted to see how well our acquisition algorithm would do inside of that space, right? But then we realized there's a lot of things that could be tweaked in our strategy, right? We can change the acquisition function. We can change the ML model that we use, and we can even change the validation data set, right? And so all of these we thought mattered. And so we decided to actually just vary them all, right? And so to benchmark everything, we chose two acquisition functions. One is our new Myopic Multiscale Sampling, or M&Ms. The other is just random search. For the validation data set, one was what we call GASB. GASB is the platform we use to generate all this data. And so this just refers to the past 2 or 3 years of data we gathered from DFT calculations, the way that we had already. And then another validation data set where we synthesized it and just kind of spent a couple of days just making up a toy data set. For the ML model, we tried 3 things. First was what we call CFGP, or convolution-fed Gaussian process. For this, some of my other colleagues actually built a neural network to predict the binding energies from the atomic structures. And then Will and I just attached a GP to the end of that. So we took the weights coming out of that network and fed them as features into a Gaussian process. And it came out calibrated. And so we just used that. The 2 other quote unquote ML models, or surrogate models really is a better name, that we used were what we call the null and prime. The null is the dumbest model we can think of. So what we did is we took the average of the entire validation data set and then made that the prediction for everything, right? And so this is really to give us a 4 performance, right? And then the prime is what we'd imagine what a perfect model would be. So this model absolutely leaked all the data. And so every time we queried it for an energy, it just gave the true answer. And every time we queried it for an uncertainty, it gave it some arbitrary low uncertainty of like 0.1 or something like that, right? And so what we really want to do here is to give a measure for what's the window of performance we could have here, right? What's the worst case, what's the best case, and what's something that we'd actually expect. So we ran these simulations, and here are some of the results, right? So the x-axis are the batches of requests here. And so this is really just each single batch is 200 DFT queries, right? So after we did 200 DFT calculations, we retrained our ML model, redid acquisitions, and then got more. The y-axis here is the F1 score on the top, as in it's a measure of how well are we predicting which materials are actually good versus are not. And when we say actually good, we mean we take our full validation data set, just chop off the top 5 or 10% or so and say, okay, these ones at the top are good and the ones below it are bad. And we just want to see how well our classifier is doing. And then on the bottom here is the delta F hat, which is a calculated measure of how much our F1 score is changing. The reason we have this is because when we're doing this, like quote unquote in production, we have no idea what the F1 score is because we don't know the answer. So how are we supposed to like see when it converges, right? And so this delta F metric is something we can actually calculate online. So this is our estimate. Okay, is our answer actually changing much as our time goes on? And like, are we converging on some answer, right? Now the lines here, all of the solid ones correspond to M&Ms. All of the dashed ones correspond to just random search. All of the gray lines use the null model or the stupid model. And all the green lines use the perfect prime model. And all the blue lines use the CFGP, right? And so there's a lot to digest here. I'm sure you guys are having fun. But one of the things that we found is obviously M&Ms generally did better than random searching, right? As in solid lines are above dashed. Another thing we notice is that when we look at the models, the CFGP is actually a lot closer to a null model than it is to a prime model, which means our model wasn't actually that good or that helpful at helping us find things, right? There's a lot of room to improve here in terms of ML modeling. And so that was a really big insight for us of like, there's so much space here. And then here you can also see that for F1 score, everything converges pretty fast by everything. I mean, these, and we can see with the delta F that ideally we should have stopped here, but you can see that it takes a long time for this delta F metric to actually start leveling out or decreasing, which suggests that if we ran this in situ, we would probably actually converge faster than we think we are. But again, this is a very biased data set, so take that with many grains of salt. Now, we can also look at the same analysis with the other data set. So this one was our gas speed data set, right? As in our real data. This is the simulated data set. And here, things are a little cleaner. You'll notice that we don't have CFGP in here because CFGP requires an atomic structure, which we did not have when we synthesized data. And so it's kind of like a invalid, if you will. So we just took it out. We don't have that data. But what we see here are lots of other interesting artifacts, right? And so one thing we notice is that the starting point, as in the starting quality or the F1 score more or less immediately, was really controlled by the quality of the model. Right? So the prime model immediately jumped up to 0.6 of F1 score, and the null started around 0.2 and climbed here. So what this says is the better your surrogate model is, the better you will start out at in your active learning loop. The other thing we saw that, which also makes sense, is that the better your acquisition function, as in if you're using M&Ms, the more acceleration we saw in terms of convergence, right? And so you see the dashed lines just take a long time to climb up, and the solid lines kind of jump up earlier and flatline here, right? And so this makes sense. It was just kind of interesting to see in another case study. Are there any questions here? All right. So that was the end of that work. We wanted to actually implement it, but by that point, Willie was finishing his postdoc and I was graduating. And so we left it to others to kind of implement and see if they wanted to use it. So now I'll be going over some other work in the materials informatics community that's been going on with active learning. First, obviously going to advertise a little bit about some of the work going on over in Toyota Research Institute, or TRI. One of my colleagues, Joy Montoya, had built a very similar system that we did with gas speed. But instead of absorption sites, he's looking at the stability of materials in general, right? So he's not doing surface work, but he's just doing like kind of the 3D structures work and trying to look for 3D structures that are stable. There's a lot of really great work he's done. And so he used very similar methods of just Bayesian optimization and other similar acquisition functions to find stable materials, right? He also extended it with one of my other colleagues, Perry, to do to accept multi-fidelity inputs, right? So the vision here is to not just do DFT, but also do experiments in tandem, right? So what if we can actually hook these two up online? And so we could do a bunch of DFT calculations, and as soon as there's enough kind of work there to suggest that, hey, this might actually be work for an experiment, then we can actually go do that experiment, right? They built the software framework to do this, but we're still unable to find experimental partners to actually do a lot of the engineering and hook this up. So this is just an idea. It's not a unique idea. Others have thought about it, but no one has actually taken this step to build it yet. Just through, I suspect, just sheer engineering effort of setting up this infrastructure. It is non-trivial. Some other work that's going on in the field is really just benchmarking, right? And so early in the talk, I went over, like, we had our synthesized data set, we had a really biased data set, and so people like Alana Spuder-Kuzik are putting an effort to really try and just make data sets for people to benchmark these active optimization algorithms on. And Olympus is his manifestation of this, right? And so you can read the paper on it for more details, but the gist is he's looking at lots of different chemistries and applications and trying to build databases for people to do these tests on, right? And another caveat is, obviously, all the results I showed you around our active learning algorithm were really specific to, I guess, that data set, And so what this does is offers people kind of a spread of things to look at. In addition to that, there's other benchmarking databases coming out. So one of our collaborators, Anubhav Jain, at Berkeley Lab, has something called MapBench, where it's less tailored for active optimization, but more for machine learning modeling in general for the materials informatics community, right? And so they have an even bigger database of a lot of things going on. And really, this is, I feel like this is the foundation for people to actually start trying to be a little more quantitative and comparing their acquisition functions and models. So I think this is really a step in the right direction here. Another thing I wanted to mention is that even though it is harder to actually set up experimental active learning workflows, there's more and more of it happening. And we actually funded some folks at Carnegie Mellon. Venkat Viswanathan is the professor. Adarsh Dev is the student doing a lot of this work. The gist is, instead of doing this active learning loop in silico with DFT, they did it completely in situ in an experiment, trying to find electrolytes for batteries. And you can see the work here, but these examples are starting to pop up more and more as people become better at robotics and start integrating all these things. And robotics itself, even without the active learning loop, is becoming more and more common in the field. One example is John Gregor at Caltech. He's doing crazy things like making multi-element alloy plates. So for example, let's say we want to make a gold, copper, palladium alloys. We can actually deposit them on like a very small sample, but in a gradient, so that if you look at all the way over in this corner, it's pure gold. If you look all the way in this corner, it's pure copper, and everything in between is here. So this is an example from some of my colleagues at CMU, but John's samples are kind of circular plates. And so what you can see here is just a huge distribution of different types of alloys that we can effectively test, right? And so we're actually working with him right now to set up a robotic system to sample different points here. The gist of why I'm saying this is that with robotics getting easier and easier and more people interested in solving these, there's a lot more room for people like you, people that are experts in active learning, to kind of step in and help design acquisition functions and really craft and have an influence on what's going on here in the materials and energy space. All right, any questions there before I move on to the last section? Last, I want to finish with some discussion topics, as in things that are still open issues in the materials and informatics space. One is, I feel like we could do better at actually judging whether or not we're helping, right? So there's metrics like the acceleration factor or enhancement factor, where like we can see, okay, how many fewer experiments do we need, or how much faster can we get to an optimum? What the thing that those things don't account for is how much time it takes us as humans to do this, right? So how many human hours does it take, or what's the calendar time, right? Because all those metrics we're looking at now, really the starting point is we've built the entire infrastructure to do this. But building that can take years sometimes and is like very costly, right? One example is one of my first papers my advisor had around the high throughput work is he took, I don't know, like a year to build a high throughput framework to do a lot of calculations, submit the paper, and then the referees were like, oh, what happens if you just do this by hand? Do you get any different results? And then he did it by hand in like 2 months and compared it, right? So it took him a year to automate something that he could do by hand in a couple of months, right? And so obviously it's the gap is closing as time goes on, but really I feel like the community could do a better job at really measuring how well we're actually helping, right? And so my colleague, Joey Montoya, had a very similar thought. And so he looked at a database called ICSD and really wanted to plot out how many stable materials, how many stable order materials that have been discovered or put into the database over time. And he plotted that alongside the number of researchers it took to find those, as in the number of authors on these papers, right? And you could see that they kind of go together, which suggests that our time efficiency is kind of staying the same, right? And so I think this is a really difficult question to answer, but it's something that I feel like we should all keep in mind of, like, are we actually accelerating things, or are we just spending our time differently, right? Another topic that I want to mention is objective functions are often ill-defined. So I've mentioned this in the talk before, but in material science community, at least, there's a lot of people using Bayesian optimization. But like I said before, when we're optimizing, it's generally best to optimize downstream, where we know everything is set. But what happens often here upstream is we optimize it, we find the best catalyst, but then we pass it downstream and say, oh, this is too expensive, or oh, this is actually toxic. You know, something crazy happened that we couldn't foresee and it's thrown out. So we just spent a lot of time trying to climb to the top of the performance peak when really it gets thrown out for some totally other reason. And so here is where I go back to the idea of we need to fail fast. And for failing fast, we don't need to optimize. We can relax our problem to some levels of estimation or something else, right? And so the point is we should really think hard about the objective function we're using and design our acquisition functions around those. We shouldn't always turn to optimization, right? Another issue in the materials community is once we go from simulations, which can get data sets of thousands or millions sometimes, and go to experiments where we get dozens or at most thousands for these robotic setups, there's just a lot fewer data points, right? And so a lot of the surrogate modeling we do really depends on how much data we have. So neural networks are fine in the millions, but training a neural network on 20 data points isn't really recommended, right? And so one of the issues that I think unsolved is really how to bridge the gap and to address the fact that, like, we actually just can't get that much experimental data. And if we can't get that much data, what tools should we be using? Like, is active learning even the right thing to do here, right? And so this is something I've been thinking about a lot. I've random ideas, but I think the community could use more eyes on this topic. Okay. The last one is, it's pretty easy to stay in our silos, right? And that's one of the things I'm really thankful for with this group. And so materials community, we know all the other materials people, but I feel like we don't read enough about people in the bio space or the tech space or the anthropology space for that matter, or something like that, you know. And I feel like folks like you, who are the statisticians and ML engineers and everything that can bridge all these applications, are the perfect route to cross-pollinate different methods and thoughts and ways of thinking. So I just want to thank you guys for organizing all of this, and I appreciate being able to see all this diverse kind of work. And with that, I'll take any more questions or discussion.
Yeah, so I have actually a ton of questions.
Yeah.
So I wonder, so I wonder about this t-SNE plot that you mentioned.
Yeah.
So quite often, for example, let's say that we have this GP model that you mentioned that didn't work that well. It was actually a quite bad model. So I assume that for the t-SNE representation, you would actually use this GP, right, to create this, or use the features. or these embeddings that this neural network provided, right? To do.
Yeah, that's a good question. We did not. So when we made the TSNE, we hadn't even created the neural network at the time. So we didn't have those as features. For the teapot model at this, which is what we had at the time when we made the TSNE flag, our features were just like a 16-bit vector effectively of like the identity of these atoms, the identity of these, and like the electronegativity and stuff. We tried using those as features for TSNE, but it actually came out just like clustering by electronegativity of a molecule, which really wasn't useful. So what I ended up doing is I made a new set of features strictly for TSNE that were composition based, because that's what I realized is what we cared about, because we can't go to an experimentalist and say, use a metal alloy with electronegativity of 0.5, right? Like that doesn't mean anything for them. For them, it's use copper, use aluminum, use palladium.
And so wouldn't this be a good feature? Wouldn't this also be a good feature for the ML model then?
It actually did not work as well as these electronegativities and all this other vector of information we have.
That's surprising.
Yeah.
But indeed, this is a big problem that I often encounter, that when you suggest somebody something, right, you cannot say to them, yeah, because of this number here, electronegativity, yeah, but this doesn't have any intuition, so why should I trust this model?
Yeah.
So this is some problem that I definitely encountered. And this is an interesting problem that I also feel like I would add on top of the many things that you mentioned, which I mostly agree with. That it's a problem that sometimes the solutions that these algorithms suggest are not interpretable.
Yes, exactly. Yeah. Victor?
Yeah, thank you again. Thank you for the talk. I hope you can share the slides later.
Sure. Yeah.
Great. Mike, like regarding the product cycle that you share, you know, this timeline.
Yeah.
Like I know that, for example, in organic chemistry, when they try to sample new molecules, when they're trying to, you know, discover new drugs or something, one approach that some people take is to ensure feasibility, they sample processes instead of sampling atoms or bonds or things like that. So that in the end, when you have a sequence of processes, then you're almost guaranteed by construction that you're going to be able to make that molecule. And so maybe that helps, you know, failing earlier, or at least not proposing things that are never going to be feasible. And so I guess the very open question is like, do you have any intuition of something similar that could be applied in the catalyst space? Like, it's not a very precise question. It's just it rang a bell as you were saying, like you want to fail fast, and I thought that this idea in organic chemistry was pretty smart to ensure feasibility. It kind of requires a dictionary or a cookbook, right?
Yeah. That's a really good point. I'm not sure. So when you say processes in the bio and kind of chemistry world, do you mean like processes for like synthesizing them? Is that what you mean?
Yes.
Yeah. In the computational like DFT space, I don't believe we have that. At least I can't think of any. For the experimental space, that seems more translatable and feasible. I haven't thought about that. I think that's a worthwhile idea, thinking about more. I don't have a good answer, but my answer is I'll think about it. That seems like a good idea.
Thank you.
Thank you.
So I think what we can do, we can stop the recording now, and then if there are some other questions which you don't want to be recorded, can be asked.